Swayam Prabha. Digital India. Educated India.
Welcome to the lecture on Introduction to Heat Pipes. We will continue the discussion on heat pipe performance analysis in this lecture. So what we will do is we will see the design features of heat pipes. We have just been introduced to heat pipes, but we don't know the entire construction details and the pressure profiles, etc. And then we will also see whether heat pipes, what are the limitations. We have seen that it's a superconductor. But does that remain a superconductor in the entire operating range of temperatures, or there are limitations to how much heat a heat pipe can transport from location A to location B? So in this limitations, there are several limitations, in fact, which are the origins of which will depend on the operating temperature and the heat flux at which we are operating. We will be looking at the most important limitations, which is called as the capillary transport limitation. As you are aware that the capillary wick which we use to construct the heat pipe, the pumping is achieved because of the capillary material and because of the capillary action. Therefore, this capillary action depends on the surface tension of the fluid and the radii of the capillary. And we will see what are the maximum limitations of this pump, because this cannot, as you increase the heating input to the heat pipe, the amount of vapor generated goes on increasing. And since in steady state the amount of vapor flow must be equal to the amount of liquid which is coming back to the evaporator from the condenser, so m dot v and m dot l, they have to match with each other. And as you keep on increasing the heat flux, the m dot v keeps on increasing. There is a demand on the pump to bring this liquid back to the evaporator, and we will eventually reach a limit after which the pump will not be able to cope up with the demand. So we will see that in this lecture also. So just to recapitulate, we have seen the construction of the heat pipe, and we have also noted, I will quickly follow it again. We have seen that the liquid pressure and the vapor pressure at the evaporator at this location here and this location here at this location, you can see the pressure on the right hand side. So the liquid and the vapor pressure, they are sustained by this particular curvature of the interface due to the Young Laplace condition being satisfied. So at the evaporator, the heat is coming in, the vapor pressure is increasing. So you can see that is the highest pressure of the system is the vapor pressure. The liquid and the vapor are separated by the interface, and therefore because of the curvature there is a pressure difference, which in fact we will see is equal to the capillary pressure difference, which is supported at the evaporator. Now in the condenser, as we have noted, it's a cold heat sink is there, and the heat is being removed from here. So Q dot is going out, here Q dot is coming in, here as you see the vapor pressure will be lower because of the lower temperature, and the vapor will flow from the high pressure region to the low pressure region, since heat is being taken away, there is a delta T existing, a small delta T between the outside ambient, this is the T ambient here, and the inside of the heat pipe, there is ambient, yeah. The vapor will condense, and since flooding conditions are here, the radii of curvature will be very large, in fact, and the vapor pressure and the liquid pressure will tend to be equal here. If they are absolutely equal, then this meniscus curvature will be flat. So as you can see, the meniscus curvature is rather small in the evaporator section in this region here, and in the condenser region it becomes flat, and naturally the liquid pressure is higher here, and now because there is a higher pressure, the liquid will flow towards the evaporator. It will be sucked towards the evaporator by the capillary pump. And typically the effective length of a heat pipe is taken as the half the evaporator length plus half the condenser length, and whatever is the adiabatic section in between, if at all there is an adiabatic section. So this is what is LA, and this is also taken to be the length. So on an average, the vapor will travel this distance, half the evaporator, half the condenser, and the entire length of the evaporator section. So this is the effective length. So this here, the pressure profile which you see here is a standard heat pipe pressure profile, and you should remember this pressure profile. This is the way a heat pipe operates, and as you can clearly see, the capillary pressure difference is the one which is guiding or which is sustaining the flow in the passive mode. So the vapor is moving towards the condenser, the liquid is moving back from the condenser to the evaporator, and this motion of this entire motion of the liquid or the fluid, vapor going towards the condenser and then the liquid flowing back, this is driven essentially by this pressure difference. So this is the pump. Okay. So naturally, as you keep on increasing the heat flux, the mass flow rate of vapor increases, and the pressure drop here increases, and then finally it will not be able to sustain it because it will go beyond the maximum pressure which can be generated by the capillary. So we will see that in the capillary limitation. Now, the first question which we have seen in the last lecture, that you have to choose the working fluid as per the operating temperature at which you would like to operate the heat pipe, and therefore which fluid to use, and how will it be useful in a particular temperature range. One can do with a figure of merit. So this is the first thing to do, which fluid to use for a given application. As you can see here, we have plotted what is called as the figure of merit for various types of fluids, and you can see that. So how do you define this figure of merit? It suggests the optimum operating temperature for a given fluid, and you can imagine that since you need a capillary suction, your surface tension of the fluid should be high. Also, you want a high latent heat substance, and the density should be also high, because that will ensure that the amount of inventory of the fluid inside the system is low, and for a given mass, you have a lot of latent heat. So essentially, rho into sigma into HFG, this comes into the numerator of this figure of merit, and naturally the viscous forces are of the two fluids, in which the viscosity of the liquid is the dominating one in the porous media, because the liquid is flowing inside the porous media. So this particular let's say viscosity of the liquid is the dominating dissipative force, leading to the dissipative force or contributing to the dissipative force, which has to be overcome by the capillary action mostly, because you have to pump the liquid through the porous media. So this sucking of the liquid through the porous media towards the evaporator is done because of the capillary action, which is attributed to the surface tension and the radii of the capillary structure, porous structure. So essentially, if you put the units of rho, sigma, HFG, and mu, you will see that the figure of merit comes in the units of watt per meter square, which is like a flux. So it actually is an indicative of the flux which can be transported by a particular fluid, and the relative magnitude of this at different temperatures and comparison with different fluids. So if you take now, naturally you cannot use a fluid below its freezing point, because it will freeze inside the heat pipe. So that is not recommended. In any case, you want the heat pipe action, which is because of the liquid and vapor movement. So any solidification of the liquid inside the heat pipe is actually not, we are not interested in that. And you also know that as you go towards the critical pressure, the HFG reduces. So you can see the sigma also becomes nearly zero at the critical point, and the HFG also becomes zero. So essentially, the figure of merit will, go as towards zero as we go towards the critical point. And naturally, freezing point, it doesn't make sense. Usually these are plotted in between these two limits, and we don't go all the way up to the limits because the maxima, as you can see, comes somewhere in the central region, in the depending on this combination of the property rho sigma HFG divided by mu L, and one can see that for low temperature fluids or cryogenic fluids, you get a you get a curve like this here. Then acetone, ammonia, water, they are at the mid temperature region, and then lithium, potassium, silver. Similarly, you can also do it for sodium. And these are, of course, are plotted by taking the thermophysical properties of these fluids from the standard thermodynamic data books, and at different temperatures. You can see at different operating temperatures. So what we see here, that these curves are of general nature like this, and typically the maximum flux, that means the maximization of the numerator and the minimization of the mu L will take place at a certain temperature range, and this is a sort of a good operating range for a particular fluid. So for example, water, as you go beyond 550 Kelvin or so, the figure of merit drops drastically. I will clean it up so that you can see it clearly. Similarly, ammonia, the maxima comes somewhere here, and this is about 350 Kelvin or so, and so on. For lithium, the maxima usually comes here somewhere at about 1200 K. So in this way, you can sort of get a feeling of which fluid to be used. Of course, as I said in the last lecture, there are compatibility issues also. So when you're choosing the right capillary material and the right container material, and also the end caps to seal the heat pipe, the welding, brazing material, all that should be compatible with a given fluid. And this, whatever at whatever temperature you are expected to operate the heat pipe, one should design in such a way that the maximum conditions of the figure of merit actually are coming in that operating range which is desirable for that particular heat pipe to operate. So this gives, of course, you will also notice that this is just the fluid selection. That means the geometry selection has to be done by understanding the limitations of the heat pipe, the given space, the volume which is available for you to complete the electronic package, for example, or what is the distance between the evaporator and the condenser, and all these factors will go into the design equation, which we will take up soon in this lecture, to complete the selection process of the fluid as well as the geometry. So the fluid part is taken care of by figure of merit. So I hope you have understood it. We'll proceed further. And now let us look at the whole process of heat transfer in a heat pipe. So as you can see, I have just made a cartoon of the evaporator porous structure. So you can see these are meshes, for example. So this is the metallic wires which are like porous media, and then there is a interface there, which is the liquid interface, which saturates this wick, and so the liquid is all filled up in the spaces inside this porous media wherever there are spaces, and then heat comes in from the evaporator. It has to travel through the condenser, as can be seen here, through the metallic tube, as can be seen here, and then it goes to the porous media, then vapor is formed, then the vapor has to travel towards the condenser, and then it condenses here, and the heat has to go out of the container. And naturally there is a contact resistance between the wick. This is the wick and this is the tube material. So if you see the cross section area, then this is the tube material. Outside, if we are talking about a cylindrical heat pipe, and then there is the porous media which is inside this, like that, and then there is the vapor space. Okay, so this is the construction. So as you can see, we have talked about resistances of different types which are encountered in this heat flow. So let us look at the resistances R1, R2, R3, R4, R5, R6, R7 and R8. And then there are two parallel resistances, the solid resistance in the tube and the resistance because of the heat which is taken by the vapor from this location from here to here. This is the vapor flow resistance, which is R5. Okay, and the R solid is because there is some heat conduction, minor heat conduction, which is taking place in this direction because there is a delta T between the tube end at the evaporator section and the tube end at the condenser section. So this is the evaporator here on this side, and this is the condenser on the other side. So as you can see, the heat has to first travel from the outside chip or microprocessor or a thyristor to the tube here, and then this heat has to go travel through the wick. So you can see R1, okay, is the outside resistance where you are mounting the heat pipe, which is in fact one of the largest, as you can see, of that order. And then comes the resistance of the tube, then comes the resistance of the porous structure, and as you can see, this is also pretty large because usually the conduction in the saturated porous wick, this wick is saturated with liquid, and therefore this is rather high. And then of course the R4 is the interfacial heat transfer, interfacial resistance at this interface when the heat has reached right up to the top of this particular porous material. So again you can see that this interfacial one is rather small, and then R5 is extremely small, and then again the reverse way takes place, condensation takes place through R6 at the interface here at the condenser, and then the heat has to travel through the wick, and then through the tube material, and then the outside thermal resistance, which is R9, and then finally Q2 is rejected, which is equal to Q1 or which is equal to Q in. Okay, so this is how the heat gets transported from location A to location B. Mind you, at the interface there is latent heat, so here it is latent heat transfer, and here again latent heat back is given to the ambient. It has to go to the ambient from here. So essentially m dot vapor multiplied by HFG is more or less the heat which is getting convected or taken from the evaporator to the condenser. So please note the order of magnitudes of the different resistances. Please note that the resistance in the wick is quite high, and in fact the internal resistances of evaporation and movement of the vapor, which is R5. So R4, R5, R6 are pretty small, and the one which dominates is of course the R3 for the heat pipe, and then R1 and R9 for the external connection of the heat pipe to the external world. So this is also very important, how you are connecting the heat pipe to the chip, which heat pipe to the heat sink, and this will respectively affect R1 and R9, which are the external contact resistances to the ambient. Now, what are the different types of wicks which are used in heat pipes? So let us look at that. We have screen wicks, we have composite screen wicks, We have axial grooves, we have slab wicks, and then there are complicated combinations which are like superposition of couple of types of wicks, which can be seen here. So you can see here these are axial groove wick heat pipes. These are extrusions of typically aluminum alloy, which provides the necessary capillary action. We will have another slide to highlight the operation. Then you have axial grooved with some slab wick which is inside here. There are these wicks which are outside on the periphery. Then there are also slab wicks combination here. We can also see screen wicks of two types. One is the coarse screen, the another one is the fine screen, and you can also see the end caps which are here, which are used for closing the heat pipe. And of course there is a valve here which is taken to the vacuum pump, and after the valve has been removed, after the heat pipe has been filled, you remove the valve and do the pinching, which has been done here, so that it provides the necessary seal for the you want to cut off the outside atmosphere with the inside two-phase system, so that there is no air ingress or there is no leakage of the material inside out, or there is no exchange of mass which takes place. Only exchange of heat takes place through the action of evaporation and condensation. So these are the different types of wicks. There are a lot of different types which are available, and essentially these wicks are characterized, simple wicks like screen meshes. These screen meshes are characterized by mesh number, which is essentially equal to if you see the mesh, it is like a cloth, metallic cloth for example, and how many number of wires are there in 1 inch, is what is denoted by the mesh number. And these are standardized. The wire diameter is given to you. So as you can see, as the number of mesh number increases, the wire diameter actually reduces. So it becomes, the porosity also comes down, as you can see, from about 75% to of the order of 65%, 65% as we go meshing it to a smaller and smaller distances. The wire diameter increases, and there are 250 wires of 0.04 millimeter in 1 inch, which denotes the mesh number. And then, as you are aware, the porosity is related to permeability. The porosity is the geometric, the porosity actually is the geometric, let's say, void which is available in a given porous material, and the permeability is the ease with which the fluid is able to pass through. And both these parameters are important for the pressure drop calculation when the liquid flows through the porous media. So as you can see, the liquid has to return inside this porous media, which is put on the outside, the periphery of the container, the inside diameter, in the inside diameter. So this is how, and there are standard equations which connect the porosity with the permeability. Usually the porosity is denoted by epsilon and permeability by kappa. And the epsilon kappa relationship can be derived for certain geometries, but for most of the geometries which are complex porous media, as we have seen different types of wicks, this relationship has to be mostly experimentally determined also. But for wire meshes, there is a straightforward relationship which can be derived, which we will also try to derive by applying the Darcy's pressure drop equation and the simplifications and assumptions. And then you can see the porosity, of course, is a geometric this can come from analytic geometry, and then through the application of the pressure drop scaling through Darcy's law, one can also derive the permeability. We will talk about it shortly in the next slides. So this is a screen mesh, as I was explaining, and you can see I have plotted the nonlinear relationship between the permeability and porosity. for different mesh numbers, and you can see typically it has a certain shape for such type of wire meshes, which we have just seen in the previous slides. The wire mesh let's say capillary structure. These are axial grooved, usually aluminum extrusions. As I was telling you, the liquid pressure drop here is considerably low. So that is one of the aims, because as you know, the liquid has to be brought from the condenser to the evaporator. And if the liquid is filled up in grooves like this, of different cross-sectional areas, you can have circular grooves, triangular grooves, trapezoidal grooves, or rectangular grooves. And they are usually, there is a saddle which you can mount the electronic component. For example, a microprocessor can be attached at the bottom here, and then the heat has to travel through this attachment uh, towards the inside of the heat pipe, and the vaporization will take place from this interface. And this let's say axial grooves will act like a porous media, where the capillary action is generated because of the opening of the mouth radius. Here the Young Laplace equation will be come in action, and this interface radius will provide the necessary capillary action which is required for the liquid to be brought back from the condenser. Of course, in the condenser, this particular meniscus will be more flat, as I was telling you, because condensation is taking place there. In the evaporator, it will get depressed, and because of this, a capillary pressure difference will be created, and the liquid will then be sucked towards the evaporator. So this is much better than a porous media, a standard porous media like a wick or a sintered copper, which a sintered material, which we are going to see next, because the liquid pressure drop is pretty high, and by adjusting the radius of this opening, this particular distance, this radii opening, or delta, one can control the capillary pressure. Of course, it is a challenge to make such type of multi-grooved heat pipe in a thin aluminum structure. So there are specialized companies who can do this extrusion on these alloys and make long heat pipes like 1 meter or 2 meters also. Naturally, as the length increases, the pressure drop will increase, and controlling the geometry here is paramount importance, because that geometry is actually leading to the pressure drop and the subsequent movement of the fluid or transport of the fluid inside the axial grooves. Then there are sintered powder wicks. You can see all the three here: screen wicks, sintered powder wicks, and grooves. Just for illustration purposes, in any given condition, there will be only one type of a heat pipe, one type of a screen mesh. And you can see here sintered powder copper mesh, which is controlled. The porosity and permeability are controlled by the pressure, temperature, heat treatment, and the binder material. So depending on the temperature and the time, you can see the porosity is getting lowered here as you go from in this direction. So you can see initially you can see the particles, then slowly they fuse with each other, and then more and more heat will make the fusion more and more closer and stronger, and there will be plastic deformation because because we are giving a pressure when the heat is being applied and the wick is being formed, and then slowly, depending on this particular parameters of powder metallurgy control, we will be able to get the desired porosity and the desired permeability. Of course, how to determine it is always an issue, as I said, for such type of complex wicks, wherein the porosity, permeability are typically have to be found out either by some electron microscopy or some microscopy, or better still by some porometer, and conducting experiments to fit the Darcy's law and try to get the permeability. So we will talk about it mathematically in the next slide. So now in this particular section, we will look at the heat transfer limitations of conventional heat pipes, how much heat they can transport if you have chosen the geometry and if you have chosen the working fluid and the wick. Then a given heat pipe of a certain length, certain diameter, certain type of porous media and a certain liquid, how much heat it can transport if you operate it at different temperatures within the limitations of the fluid which you have added. So this is what we are going to do in this particular part of the lecture. So now we will look at the heat transfer limitations. So as we have been discussing, the operating temperature of the heat pipe for any given fluid, let us say from close to the freezing point up to the critical point. So we have seen the figure of merit, and we have also seen that at different temperatures. So it depends on at what temperature you want to take the heat out. So suppose you use water and you want to take the temperature, you want to maintain the temperature at 50 degrees, of the electronic component. Then your cooling atmosphere will be of the order of 50 degrees, so that automatically the evaporator temperature will not be very different from that. It will be slightly higher, let us say, depending on the thermal resistance. If you want to take the heat at 100 degrees centigrade, then naturally the outside ambient with the circulating water or whatever ambient you are giving to the condenser should be of that order of temperature, so that the evaporator temperature is accordingly adjusted depending on the thermal resistance of the device. So as we will see that one can do an experiment, one can do a theoretical experiment in which you can control the temperature of the operating temperature of the heat pipe, which is usually the adiabatic temperature, by controlling the condenser cooling water temperature. So that is the main idea, the main way by which you can control the operating temperature. So approximately the R thermal will be known to you by a few experiments at that temperature, and then you can adjust the evaporator temperature accordingly. So when you start giving a low quantity of heat, the heat pipe operates. As you go higher and higher, as you go higher and higher on the axial heat flux, you keep on increasing the heat flux of the heat pipe. You will notice that at certain point at this temperature, the heat pipe will stop operating. Now there may be several reasons for it to stop, because of which it has stopped operation. So we would like to know these limitations of why it stops, why it cannot operate at a given temperature after a particular heat flux is attained. So now, let us assume that we know the physics of why it stops, and there are certain correlations which are available, let us say, which tell you that at a given operating temperature, what will be the maximum, heat flux which the heat pipe will tolerate. So of course people have done these experiments in the past, and it has been now understood that at different operating temperatures the heat pipe does stop at a given heat flux. As you keep on increasing it, of course you have to keep maintaining that operating temperature by controlling the condenser coolant temperature. So basically what you do is you increase the evaporator power by a certain, let's say 5 watts or 10 watts. The temperatures will rise. You will bring them down to the operating temperature which you want by cooling down the temperature of the condenser. The condenser is also usually over designed so that you are not limited by the capacity of the condenser, which itself can be a limitation sometimes. But that is, we are assuming that, let us say, that is not there right in this particular case. So as you keep on increasing the heat power and you allow the heat pipe to come to a steady state operation, by adjusting the condensing temperature so that it maintains the adiabatic temperature is maintained at a temperature of T1, let us say. And then slowly you will see that after a while the thermal resistance suddenly shoots up, and you have a limitation. That means now the heat pipe has practically stopped working, and whatever small thermal resistance was coming, now it is so big that you are very sure that this liquid vapor internal circulation has actually stopped. Okay, so this is what will happen. So now if you do these experiments or set of experiments at different operating temperatures, you will see that the heat pipe starts stopping. I mean, the heat pipe stops operating at different powers, different powers, and you will get a typically curve, like this, which means that at any given temperature, you can only operate up to a maximum Qmax, and beyond this, the heat pipe is not going to operate. So this is what is called as the available design space of the heat pipe. Now, how do you get these curves? In a sense that one can of course do an experiment, but one needs some analytical techniques also, so that these curves can be predicted. So, for example, at low temperatures, the heat pipe will stop, and the reason for it stopping is because of viscous limitation. Okay, so that is one of the limitations at low temperatures. As you increase the temperature, after a while there will be what is called as a sonic limitation. So you need a formula or a correlation to actually predict this sonic limitation. Similarly, you need a formula to predict this viscous. So given the operating conditions, given the thermophysical properties, given the operating temperature, what should be the axial heat flux which the heat pipe will go because of viscous limitation or because of sonic limitations. At intermediate temperatures, you may get entrainment. I will explain what all these limitations are in a while. I'm just giving you the names before. So you will have entrainment, and sometimes you will see that the capillary limitation and the sonic limitation and the entrainment limitation, they are close to each other, and one of them will be operative at a given temperature. For most of the central operating region where the figure of merit is usually very high, the heat pipe is limited by what is called as the capillary limitation. Once you increase the temperature further, then what you get is actually boiling limitations. That is what you get, boiling limitation. And the boiling limitation curves can be different for liquid metals, for example, and of course they will be different for low temperature fluids, and that will determine at those temperatures which one of them will be dominant, whether it will be boiling coming, or whether it will be capillary will come first and then will come the boiling. That will depend on the type of heat pipe working fluid which you have chosen and the operating temperature at which you are operating. So these curves which you see here, these red curve, this blue curve, this yellow curve, this curve, gray curve, dark blue curves, these are actually analytical expressions which have been developed to predict these different types of limitations. Now, the heat pipe can also be frozen. For example, in space, if you use some fluid and it is minus, it is facing the deep space, and you have chosen a fluid which freezes at that temperature, so it may freeze also. So when you start some heating, the liquid is not really in circulation, so there can also be a frozen startup. For very small heat pipes, you can also have a vapor continuum limitation, but we will not discuss much about it in today's lecture. What we are going to focus is the capillary limitation. This is the most important limitation, and any heat pipe designer in the mid operating range between the freezing point and the critical point, at the critical point, of course, it will come down somewhere here. Any heat pipe designer will always calculate the capillary limit, and we must understand what capillary limit is. Boiling limitation will come when CHF type of conditions are there inside the porous structure, and you have seen in the pool boiling heat transfer course that eventually you will reach, and so as you keep on increasing the heat flux at higher temperatures, eventually you will reach a point which is the boiling limitation. Similarly, sonic limitation will come when the speed of the vapor will be close to sonic speeds that usually occurs on the lower end of the temperature spectrum, And of course, if it is too cold or too low, close to the freezing point, then the heat may not be able to push the liquid, push the vapor, and you may have a viscous limitation. So these are different types of limitations. We will not go into the details in this particular course on all the limitations. Nevertheless, the most important one is the capillary limitation, which we will try to understand in the next slide. So what is capillary limitation? So as we have seen that the heat pipe, the vapor has to go towards the condenser, and the liquid has to travel back. And this happens because of, as we have seen, the capillary pressure difference between the evaporator and the condenser, wherein in the evaporator you have a finite radius which can maintain the capillary pressure difference, and in the condenser side there is flooding taking place, and the radii of curvature is really very large as compared to the RE, for example. The RC is way larger than RE, and therefore the water is able to be pulled towards the evaporator. Now the thing is that once you decide the fluid, the capillary pressure is actually decided, because it depends only on the surface tension and the radii of capillary, the radius of the capillary structure. So this delta P capillary actually gets decided as soon as you fix up the working fluid and the wick structure which you have. This will determine the capillary pressure drop. Now, if the evaporator is on the top, gravity is in this direction, it's acting downwards, then naturally the liquid has to be pumped against gravity, and therefore in such a configuration the gravity will not assist. So rather than the plus sign, we will have the minus sign there. But if you reverse this heat pipe and evaporator is at the bottom and condenser is at the top, which is the gravity supported configuration, then we will use the plus sign here, because the gravity will help you pump the fluid from the condenser to the evaporator. But right now it is at an angle, so naturally the cos theta component of the gravity will act. As the theta changes from 90 to 0, the gravity will be fully operational in 0 degree centigrade of xi, 0 degree inclination, and when it is 90, that is horizontal, gravity doesn't play a role. In fact, this will become, in a horizontal heat pipe, this term delta P gravity will not be there. So on the left hand side of this equation, which we are writing here, the capillary pressure plus or minus gravity pressure, this is the pump. Okay, this is the plus side of it. That means this is what we know, we have it as the starting point. And what is on the right hand side? On the right hand side is the liquid pressure drop in the porous structure and the vapor pressure drop in the core of the heat pipe, in the central section of the heat pipe. So if you are able to calculate these four terms, we have to always make sure that the delta P capillary and delta P gravity should always be greater than or equal to the dissipative forces, which are the negative, which is the negative part. So we have to always ensure that this particular terms are greater than this particular term, so that the heat pipe will not stop. And when that happens, when it is not, the plus side becomes, the left hand side becomes smaller than the right hand side, essentially the heat pipe cannot operate, and we say that a dry out has occurred. That means the heat pipe has stopped operating. So let us calculate all these four terms. So first we will calculate the delta P capillary, so which is equal to 2 sigma. In the evaporator side, the pressure difference between these 2 points, let's say 1 and 2, is 2 sigma r cos theta E upon r capillary, and similarly between 3 and 4 is 2 sigma r cos theta C divided by r capillary, and naturally the theta E is different than theta C, and therefore the delta peak capillary which exists between 4 and 2 is 2 sigma by r cap cos theta c minus cos theta e. And naturally, since cos 0 is equal to 1, and therefore the limiting cases, this will become 1, this should be E, and this should become 0, and therefore the maximum capillary is 2 sigma by r cap. So as I said, as soon as you decide the fluid and the operating temperature, since sigma is a function of temperature, you fix up this 2 sigma, and r capillary is fixed by the choice of the porous media. The gravity is simple. It is rho L into G into L effective into sine alpha, where sine alpha will be equal to 1 when the evaporator down or vertical position. So you will get the maximum advantage of gravity when the evaporator is here and the condenser is here. Okay, and vice versa. Of course, sine 0 will be 0. So therefore, there is in the horizontal position there is no gravity. Okay, so that is how the plus and minus sign will be taken care of by the sine alpha. Okay, so these two are the left hand side of the equation. So plus minus will automatically come when alpha is properly done with respect to the vertical. Okay, now let's look at the vapor pressure drops. Now in the vapor pressure drop, as you know it, you have already done this, the Navier-Stokes, the simplified Navier-Stokes equation for a pipe flow, and one can assume that this particular vapor flowing inside the core is more or less like a pipe flow, because the porous media is really at the corner here, a very thin porous media. So as a first simplification, we can just assume that since the porous media is very thin, the vapor more or less flows like this. Now depending on the heat, because Q dot what you give will determine the m dot vapor. So more the Q, the more the m dot vapor. So depending on that, the vapor flow can be either laminar or it can be turbulent. And the parabolic velocity profile for this equation very well. I don't have to repeat it, and the average mass flow rate of the vapor, which will be equal to the Q divided by the HFG, because Q dot is equal to mv into HFG, is what we are assuming the phase change process taking place. And then the parabolic velocity profile, the second order with the boundary condition. Now of course one is a symmetric boundary condition at the center, and this one is a sort of an artificial boundary condition at the corner. We can assume that no slip is there, so that we can get a good answer, which will be more or less correct also, because although there may be some slip, because the vapor is actually not touching the wall, but it is touching the liquid vapor, the liquid saturated porous media. So once you know the velocity of the vapor, then you can get the pressure drop because of the vapor. Then we come to the liquid pressure drop, and the liquid pressure drop, as you know, it's a porous media flow, and the dpdx is in a porous media depends on the superficial velocity, which is the velocity outside the porous media, because inside the porous media the velocities are very difficult to calculate. They will all be different. There is tortuosity, and of course the velocity will increase. There will be some acceleration which will take place in the porous media. So what the Darcy's equation tells you is that dpdx porous media is proportional to the superficial velocity. So you keep on increasing the superficial velocity, the pressure gradient will increase, and naturally if you use a more viscous fluid, the pressure gradient will be more, and therefore in the proportionality constant you get mu divided by k, and then now you can check the units of the left hand side and the right hand side, and they are equal, they are uniform in fact. So what essentially it defines is that the capital K or kappa as the permeability of the medium, and this, as we have seen in the case of screen meshes, this was done easily by geometry, but in many other cases like sintered wicks or other geometries, the K probably have to be determined experimentally, but there is enough data available in the literature. Please note that even if the porosity is the same, the permeability, which is the ease by which the fluid has to flow, is actually different, because here there are paths which are directly connecting the inlet and the outlet, but in the second case there is tortuosity, and therefore the permeability will be different in this case. So applying the Darcy's equation, and then making the equivalent, because these are complex porous structures like copper wicks and all, we will convert them into simple tubes which are of a certain geometry which satisfies the fact that going from this particular type of porous media, which is complex to analyze, we simplify in the Karman-Kozani equation into simple tubular flow, for which, in fact, we know the velocity profile, because we can easily determine the velocity profile from the uh, from the parabolic velocity profile. So what we essentially do is we make an assumption that surface area of the tubes is equal to the surface area of solid particles which are used in the porous media, and therefore if I will not go through each and every equation, but you can see that if you know the particle diameter here, if you know the number of particles, the total volume can be calculated, the total surface area can be calculated, and in this case the volume of solid divided by the surface area of the solid, and in this case the volume of the tube divided by, so you essentially want to analyze this, and you are actually analyzing this by making an assumption that the surface area of the tubes is equal to the surface area of the solid particles. So from this, equating these two, we will get uh, the the equivalent tubes. So you can see here the volume of the tube and the volume of the solid is related to each other by the porosity, and therefore the diameter of the tube, the equivalent diameter of the tube, which is an equivalent porous structure which gives the same pressure drop as the actual porous media, can be calculated. And can be related to the particle diameter. So from this, you also know the superficial velocity because you know the total flow rate. We can now use the Poiseuille equation for laminar flow, which you already know, which has come from the application of the simplified Navier-Stokes equation to the pipe flow. And what now the difference is that since the velocity inside the porous media is not known, and we have to work with the superficial velocity, we will multiply by L dash upon L, which is the average length, where L dash is the average length which the particle travels inside the porous media, and L is actually the length of the porous media. So if this is the porous media, okay, then this is L, and the actual length, the actual average length which the particle passes through inside the porous media, is actually L dash. So in this way, the Karman-Kozani framework gives you the relationship between the standard velocity profile and an equivalent model of the porous media, and therefore if you compare these two equations, you will see that the permeability actually is given by this particular value, 72 into 1 minus epsilon square divided by epsilon cube into L dash upon L into dp square. So what I am trying to say is that since L dash upon L is not known, dp square is also not usually uniform. It is not a single morphology. There are different particle sizes. So this particular equation, although it is mathematical by comparing the flow in a tube equivalent model to the flow in the actual porous media and applying the Darcy's law, you will see that this particular highlighted portion actually is a representation of the permeability if you compare it this equation with the Darcy's equation. So naturally the L dash upon L is usually greater than 1, and therefore this number 72, which has actually come from pipe flow equation, from the Poiseuille equation, this 72 number may change, and depending on your porous media, this number can change anything between 100 and from let's say 72 to even of the order of 220 or 250, and therefore, as I said earlier, the permeability has to be calculated. The permeability has to be experimentally calculated. So applying the simplest capillary limit, on the left hand side you have the capillary pressure drop, you have the gravitational pressure drop, this is the plus, and on the right hand side you have the delta P liquid, which is coming from the Darcy's equation, and the delta P vapor, either it is laminar or turbulent. You know from standard pipe flow equations, depending on the Reynolds number, one can please mind that this Q is coming because the m dot vapor is actually directly related to Q divided by HFG. So in this way, you know, the vapor velocity, and in steady state, naturally m dot V is equal to m dot L. So from there the m dot L is also known. So that is how the Q comes into picture. So as you keep on increasing the Q, the m dot increases. Because the m dot increases, the liquid pressure drop increases, the vapor pressure drop increases. So the dissipative part is completely increasing as you go on increasing the heat flux, because the axial Reynolds number of the vapor flow is also increasing. And on the left hand side, these two are fixed. Because the capillary pressure drop only depends on the thermophysical properties, and the gravitational pressure drop depends on how you have oriented the heat pipe. So essentially, the plus sides are fixed, that is the pumping power is fixed, and the dissipative power is the dissipative energy or dissipative power requirement is actually increasing as you keep on increasing the Q, because the m dot keep on increasing, and that changes the pressure drop. So essentially what is clear is that after a particular while, when the Q increases to such a value that the pumping heads are not able to, so this equality actually is fine. Up to equality is fine. So far as this is greater than, the left hand side is greater than, fine, the heat pipe will operate. As soon as it becomes less, there will be a dry out. So this is what is the main message. So you compare the two, and one can get the Q max, you know, which will lead to this particular inequality to hold. So if you do this for different types of meshes, by taking some heat pipe and some copper water this thing, and then take some porous media, you know, you can get curves like this, which are actually what are called as the design curves. That means, let us say if you take a screen covered mesh, you know, and you are operating at 160 degrees centigrade, then you can actually you know, only transfer about 4,400 watt meter of heat in a real heat pipe. In actual practice, of course, there is some recovery also. As you can see, this graph you have already, this pressure distribution is a simple pressure distribution, but in reality, as you will notice, that as the vapor condenses, there is some pressure recovery. So the pressure doesn't continuously decrease like this, but there is also some recovery which can happen because of the deceleration of the fluid. Also in the evaporator, the mass flow rate is not uniform throughout the evaporator. As you proceed in this direction, the mass flow rate increases, and therefore you get a non-linearity so these are the real profiles which you actually get in a real heat pipe. But the theory which we have just studied it can give you pressure drop of that type as shown on the top here, which is the ideal profile from this type of let's say analysis. We will not go into the details of how to get the secondary acceleration and deceleration effects, but it will suffice that you are able to calculate the maximum heat flux at a given operating temperature for a given heat pipe for which the working fluid has been chosen and the geometry has been chosen. The L evaporator, the L condenser, and the L adiabatic section is chosen, and then you are expected to find out the maximum capillary limit, which is the Q max from the theory which we have just learnt. So coming to the end of the lecture, we have seen how to evaluate the performance of a heat pipe. We have derived the capillary limit of a conventional heat pipe. The other limitations we have not touched, but we have understood them, and we have learned to plot the performance curves of a wicked conventional heat pipe. So with this, we come to an end of this lecture. And thank you very much. If you have any questions, please don't hesitate to write to me. Thank you.